What's up, hackers? Welcome to Chill Code. My name is Taggart. I'm going to be real honest with you. I don't have much of a plan for tonight. There's a whole bunch of kind of tiny things that I wanted to poke at. And so this would be the stream equivalent of when, a teacher puts on like a video. Maybe not the most intense evening, but that's okay. We'll still have a good time. I've been threatening. Hey, Angel, good to see you. Yeah, obviously, get the rest that you need. Don't sacrifice your sleep for Twitch. But I've been threatening to do some more Haskell on stream, and I think we're going to do that. As I was poking around, yes, Gingerroot, it's happening. As I was poking around looking at Haskell resources, I noticed that Exorcism has updated one more time. There have been now 3 versions of Exorcism, and we're now on version 3. And this is actually pretty rad. So Exorcism has historically been a command line interface type tool, which I actually appreciate because it made you learn the command line interface in order to use the thing. They still have that option, but they also now have an in-browser editor, which, given the amount of languages that Exorcism is dealing with, is no mean feat, and actually really helpful to get started, especially, some of these languages, there's a lot of stuff to install. So pretty cool, and we are going to take a look at some Haskell just to get my Haskell muscles back in gear, and remember how to do stuff with it. So we're going to do some of the early exercises in Exorcism, get a feel for it, and then kind of move on from there. There are a few other things that I think we might touch on tonight. But if you want to play along, getting started with Haskell is actually super easy, and easier than I think people might give it credit for. So if you go to haskellstack.org, that is kind of what you need to do to get started. I love that it's a redirect, but yeah, if you go to this link right here, haskellstack.org will do it for you, but there's the actual link that it redirects to. And if you're on a Linux or Unix machine, so this will work on Mac too, go ahead and do this curl, and it'll handle the installation of Stack for you. What is Stack? Great question. Stack is not just the GHC, the Glasgow Haskell compiler, but it's also a handful of other utilities that Haskell uses to make this kind of a modern programming environment. That includes Stack. It also includes Cabal, which is the package manager, and a few other things as well, including GHCI, which is the REPL basically for Haskell. So Haskell is a compiled language, but GHCI allows you to run individual commands and test certain things out one by one without having to compile things. So super, super, super handy. And so Stack is kind of like the main tool that you would use for all of this, although you can also directly call GHCI. For example, if I were to call GHCI here in my terminal, you can see that I get an interactive Haskell terminal. And if I did let's try words. This is how we split strings. I think that's just so cool. I just find it super elegant. Remember that in Haskell, as a functional programming language, everything is a function. So the definition for words is that it takes in fact, can I do type words? Yep. God, I love this. There's just something so beautiful about this. But yeah, so what we're looking at here is the function signature for the words function, where it takes in a string and returns a list of strings. And this is how we often search for things in Haskell, is by the function signature. So we want to know what the data type coming in is, what the data type going out is. And thinking about data types just makes you a better programmer. It's one of the reasons I'm so aggro on using Haskell, at least as a training tool for the programming mind. Okay, so we're getting started. We're going to start off with the hello world. This shouldn't take long at all. If it does, we're in trouble. But what it will do, in addition to getting us familiar with the kind of the ergonomics of the language, is introducing some of the Haskell build tools. So I have this set up here. I have it installed. Yes, I could do it in the editor, but I'm doing it in VS Code because I want to do it the way I normally do. So first of all, take a look at this folder here. You can see that I've got a stack.yaml and I have a package.yaml as well. These are the things that Stack will use to actually build the project. Very much like cargo in Rust or npm in JavaScript. It's really not that different. And this is the kind of stuff that we use to modernize a pretty venerable language like Haskell. Now, one of the things you'll see is hspec, and this is the testing library. Hey, Destroy Worlds. Yeah, so hspec is the testing library, and so Exorcism, despite its new version and its facelift, is still really an exercise in test-driven development, meaning that they give you the tests to run, they'll fail first, and then you have to figure out how to implement your solution to pass the tests. And you can take a look at the tests as well. And this tells us a little bit about how this works. So the test we see is that it imports hello world, and it's importing the hello function from the hello world module, which is right here. And basically we just have to have this return us the correct string. So this one's about as easy as it gets. Hello world. Before I save that, I'm going to run stack test just so you can see it. Zoom that in just a little bit. And it compiles, runs test, fails. Right? Expected hello world, but it says goodbye Mars, which makes me think of Commander Keen. But, so if we change this up, save it as hello world, we should pass. It's recompiling because it's, different now. And it passed. Not particularly difficult, but let's take a look at the shape of the language here. So with every function definition in Haskell, we're going to say on this line, we're going to say this is the function signature, just like we saw for the type earlier, where we looked at the type of words. See those double colons? So after that comes the function signature. And also, the function signature will also indicate any arguments that the function will take. You'll see that in probably the next one that we do. There's a fun thing about the theory that backs Haskell, which is that essentially the idea of currying, we'll get into what that means, but Haskell doesn't really differentiate in its notation between taking a single argument and multiple arguments. It just uses arrows the whole way to the destination. And we'll talk about why that is. Okay, so we passed our first test. We'll do exorcism submit source hello world.hs. Great. So we're good with that. We'll close all these up. We'll move on to the next one. I definitely just completed it. Yeah, mark is complete. I don't really feel like sharing this with the community. It doesn't really matter. Show me more exercises. So here's the deal. This feels very teachy to me, which is great for learners. It's kind of getting in my way because I know what I want to do next. But it's actually really great. There's a lot of scaffolding around here to help you out, including sharing your solutions with the community. That's a really important part of Exorcism for me, is how it does that. Let's do RNA transcription. I think that's a really good one. Again, real simple, but we're going to learn a little bit about how this goes. So we're going to download the exercise. And we're going to run stack test first to see what fails. Okay, a lot of stuff fails. 2 RNA, empty RNA sequence. You need to implement this function. Okay, well, that's a good reason for it to fail. We haven't implemented anything. Let's go to the RNA transcription. We'll get dna.hs. Sure. Ooh, interesting. So this, let's take a look at the type signature that we are given here with 2 RNA. So a string comes in and then an either type is returned. This is super interesting. We got one exercise into Haskell before we can talk about monads. So, and monads, if you've heard about Haskell at all, someone's probably like made a joke or groaned about monads to you, or you've seen that in the conversation, like the Haskell discourse. Don't sweat them. We've actually seen them a lot on this stream in another language. We just never talk about it. And that would be Rust. Rust uses monads, basically. Whenever we have a result or an option where it's like either it's the value or it's an error and we have to handle both possibilities, we're dealing with monads. So don't sweat that idea. But this either is really, really cool as a type. I love ethers just because they make reasoning about things pretty elegant. Let's check out either in our Haskell documentation. And yes, the documentation searcher for Haskell is called Hoogle. So this is a little bit in the weeds here, but what are we talking about with an either type? An either type is either whatever is defined as the left type and or the right type. So when you create an either, you need a left and a right, and they can be any type you want, but that's how we define it. There's a left and a right. Think of it almost, if you're familiar with binary trees, right, where we're creating two possible branches and we're going one direction or another. That's really what we're talking about with an either. And if you wanted to implement a binary tree manually in Haskell, an either would be a great way to do it. So it's an either A or B, and we can do a match against whatever type it is. So that's kind of interesting. But how are we using it? How are we using it? Either a car or a string. Why does that matter? So it's either a car or a single character or a string. And in Haskell, much like in other languages, strings are not special. They are just lists of characters. In fact, let's fire up GHCI one more time. I should probably just load that up in a separate tmux window so we have that available to us. And we do type hello. It'll tell us. See, it doesn't tell us that it's a string, right? It tells us that it's a list of type car. If we do type, by the way, in double quotes H, it still says that. If I do single quotes, however, it says that it's a car. So much like Rust is sensitive to single quotes, double quotes, so is Haskell. So be aware of that. Okay, but why does that matter? Why would we have an either character or string? Meaning that Angel, I say it is car with a hard K rather than a ch sound. I don't really know why, because char is a word, right? As in to scorch, to carbonize. But I say car because it's short for character. I don't know. I don't know what my internal reasoning was for that, but yeah, I tend to do hard K. Also, char was a race in Guild Wars, if anybody played Guild Wars. That used to take up an upsetting amount of my time. Angel, I can't tell how you say it when you write it. But I assume it's the opposite of what I said. But no, so this is really interesting because this is ripe for recursion. Destroy worlds if you're still there. That's for you. And this is often a pattern that you'll see in Haskell programming, where if we have a big problem, what we want to do is try to reduce, and we can reduce it to smaller iterations of that problem. We will do so not with iteration in the way that we normally would in an imperative programming language, but through recursion, meaning that we're going to use this function and kind of break it down piece by piece, and then we'll have a base case, meaning when we can't break it down any further, what do we return? That's kind of like the Haskell way. So why that matters is that as we recurse through this function, we're going to either be returning a string or we're going to be returning a character. And the character presumably would be the last one. So that's kind of interesting. So let's see here. Let's first get this thing passing, meaning running, failing still, but to RNA, notice that we have this is a single argument. It's just a type definition, or sorry, this is the argument, and then this is the return. So the argument is actually being called x's, which again is super Haskell-y, to call it the plural of a thing. And they're not Haskell programmers, because they're mathematicians generally, are not super explicit with their variable names. Now, I should say that is an academic Haskell. I actually haven't seen a whole lot of production, industry Haskell, so if they are, then awesome. But generally speaking, you're going to see tiny variable names like this. And we might re-implement this, but I want to see if we can keep their intended signature here. Either way, at the end of the day, the test that we're running for this is looking at all strings, right? And notice that the expected is right. Oh, interesting. Okay. So let's take a look at what we have here. So, and by the way, what we're dealing with is a pretty common thing. This is actually something that happens with RNA transcription, which is that certain of the nucleotides, right, are rewritten in the RNA encoding. So that, right, guanine is written in the RNA, in the guanine in the DNA is written as cytosine in the RNA for transfer. Thymine becomes adenine, adenine becomes uracil. And it's essentially because their molecular shapes are complementary. I'm basically just pulling this from AP Bio. I'm not a biologist, I have no idea what I'm talking about. But if you have a strand, TLDR, if you have a strand of DNA that looks like this, the RNA complement for information transfer is going to look like this. Which, when re-encoded by I want to say RNA polymerase? Depolymerase splits it, and then polymerase puts it back together. It's been 18 years since I took AP Bio, so I don't really know what I'm saying. Point is, these are complementary, so we're basically just doing a pattern match here. A becomes U, C becomes G, T becomes A, etc. So, right is going to be strings, and left is... oh, interesting. So we might be able to recurse this, but the either is not meant for recursion in this particular case. What they're trying to do is basically call the left an error type. And it's kind of weird that they're doing it with an either rather than a maybe, but whatever. Basically, the either, they're saying we're going to alert the nucleotide that gave us trouble. So, I think we can still recurse with this though. So we'll say let's just return x's first to see it fail, but fail for the right reason. Oh, that was wrong because I didn't give it the right type. I returned a string rather than an either char string. So this actually will still yell at me, I think, because I need to account for a right and a left return type. No? It might not yell at me. Yep. Okay, so our failures are happening, but for the right reason, basically. Trying to think about the best way to do this here. So we have to look at each one of the characters in the string and transpose A to U, right? So let's think about... Let's make a little transpose function. Up here, which is going to take a character and return a character. And say transpose C equals, and we're going to do case C of. And I want to make sure that I get the syntax for this right, because this is kind of a pattern matching thing in Haskell, but I just want to make sure that I'm getting all of it right, because it's been a minute since I've done this. Case. Yep. Awesome. Case of, like so. And then we say, so A becomes U, right? And T becomes A, I believe. Is there a readme here? Yes. T becomes A becomes U, C becomes G, G becomes C. And then we're going to give it a default case. Which is C. Which I'm pretty sure we can do. Case of their guard expressions. I really think there is a default, like an underscore, though. So we'll try to compile that and see what it does. So basically, this is still not totally correct, but we're doing this to demonstrate something. So basically, we're going to do write. And what do we write? We're going to do write. We're going to map transpose onto x's. And I'm not getting any, like, language alerts here. I feel like... maybe this this Haskell syntax highlighting is not working for me. So let me reinstall. This one here. See if the official Haskell Foundation one does any better for us. Sure does. Right. Okay, so why did the $sign help me out here? Basically, the write requires a single argument, which is the type of the value that I'm writing, I'm sending over. And it didn't know how to handle the fact that we're not using parentheses. So it didn't know, like, oh, I'm mapping the function transpose onto x's, and that whole thing, that's what we're sending back inside the write wrapper. To solve that problem, I'm using a $sign. A $sign is the Haskell equivalent of parenthesizing whatever you have until the next $sign, basically. So it's a little bit different than using the period, but this will work for us here. And it looks like our underscore is working for us the way that I had hoped. So now if we rerun the stack test, this will still fail. Actually, some of them might pass. But we're getting there. Seven examples, one failure. Are the others not getting tested? No, wow. So that actually passes all but a single test, which is correctly handles invalid input. And this is where we actually have to do some sanity checking on our input. Because right now, we're trusting that everything that we're being given is a legitimate DNA sequence. But it turns out that it's not. So we're going to write this a little bit differently. We can actually see how it was working if we go back to the I know there's a more elegant way to do this, but for now, we're going to quickly do first we're going to do a I'm trying to think how I want to do this. There is a Haskell function called member. Is it not? Ah, it must be a different value. Or a different function name. Alright, we go to Google. What I'm looking for is something that takes a car, takes a list of cars, and returns a Boolean. And that is how we're going to search for this. We could also cheat and just be like, Haskell car in string, which actually works fine. I really thought there was a function called member. All right, let's just look at data.list and see everything that we have in here. LM. Buh. Okay, so the reason I couldn't find it is because the signature is a little bit more generic than I thought. So let's go back up to our test here. So the LM function basically just looks for membership. This is essentially saying, like, if we were doing this in Python, it would be like A in ATCG, right? And this is why we have our left in our Haskell. So we're going to change this up a little bit. What we've just done is we have split the string into the head of it and the tail of it. And this is a pattern you'll see very often in Haskell recursion. And here's the trick. We're going to say to RNA Okay, it's saying patterns not matched, but that's fine. All right, we'll do it this way. Equals case, and we'll indent this. Case x of. So if it's empty, we're gonna just return right. That has to be a string. And actually, does empty... Yep, exactly right. Character literals may not be empty. Trying to think of the better way to do that. Let me explain what we're trying to do here. So we have, we'll comment this out. So we have this string that we're making, right? What we want to do is for each one of them, this string, we're going to split this up. So we're going to take the first one, we're going to analyze just that part. We're going to say, is it good? If it's good, transpose it, and then send the rest of this back around into this function. But if it's not good, if any of these doesn't, match, then we're going to give a left and say we're done. So to make that happen, we can actually explicitly do this. Still yelling at me because pattern's not matched. That's what it was yelling at me about. That's what I was trying to say before, and I was being dumb about it, which is that to do this is our base case, basically saying once we get to an empty list, we're going to return a right string anyway, or if we're given an empty string right here, now we're going to just return an empty string, no problem. Here, though, we're going to, this is interesting, to combine elements of a list. We do 1, 2, 3 doesn't work, but that does. So we can combine two lists together, interestingly, but if we combine, we can't like append the way that you're used to super easily in Haskell. Like it's possible, but see how even in the documentation, it's like we're using plus plus, but we're combining it inside of a list. It's because of the type signature thing. We're trying to work with the same type at any given time. So that's what we're doing. Okay, so case x of a equals right, and of course what we actually want is u plus, and then we're going to, this is where it gets fun, 2 RNA x's. So this is oh, wait. I needed the dollar sign there. And if I paren this, couldn't match. Oh no, that's not gonna work. We can't forward apply it. Because we're sending in either. Fine. Fine. We'll have to do this a little bit more sloppily for now. But we're on the right track. So basically, all right, the either is messing us up here because we can't. Why can't we recurse with this? Basically, if I were trying to do what I was doing before, right, where we say 2 RNA with the x's, meaning the tail of this string, what's the problem? So 2 RNA is supposed to return an either type, but I'm playing with it as though it's returning a string. But that's not the case. Consequently, I cannot recurse down the way that I want here. But I think we're on the right track. We just need to sort out how to handle that. We need this to be a string. Hmm. I am definitely overthinking this. Let's back this up a little bit. This is like the beautiful struggle of Haskell, is working through type transformation. So we know that we're getting an empty string for that, and then what are we doing for this? If we do write map transpose x's, we run into the same problem we had before, right? Where we're only returning correct values. We're not checking for evil or incorrect values here. So if we want to do a recursion on this, because we can't combine this here. Okay, here's what we could do. We could write a safety function for our evil. So basically what we would do is check the nucleotides. Send it a string, and we will say, we'll use an either, actually. Either car or bool. And with check nucleotides, we will say thanks, Angel. Have a good night. Wait, no. That was... I don't want it to do that. I don't want it to return a string. No, that's fine. Because what we have is we have an all function, and all takes, this is a little bit interesting. What we're looking at here is a type constraint, meaning that t, whatever type t is, has to be foldable, meaning that we can kind of iterate through it and reduce it from many values to one. We have a function that takes a value a of type A and returns a boolean. So basically it's a check for truth or falsity. And then an object of type t containing A, meaning like a list of A's or something like that, and then returns bool. So that's a really complicated way of saying what the all function does is it goes through a list, and if all of the elements satisfy this predicate here, then the all function returns true. If it doesn't, then it returns false. Why is that cool? Because we're going to actually, this can just return a bool, can't it? No, because I want the car there for a reason. Nope, I still want it to be a bool. There's, I'm getting there. So, checking the nucleotides, x's equals all, and then we're gonna write a tiny little lambda function, basically an anonymous function, and then we're gonna say lm n in ATCG in X's. So that's a little syntactical sugar for us here. Why not an LM? Oh, there's an infix. Version of LM. Why not LM ATCG? Okay, I will do that. Haskell has all these interesting syntactical sugars that make the code a lot easier to read. So what we've now done, the backticks, by the way, allow you to use an infix function. Now, you might notice, hey, this function doesn't have an argument, a parameter coming in. It's implied, is the way that works. It's implied by this. So basically it's saying whatever the thing we send it to is going to get fed into like the left side of this. And also to the argument here. Or actually, I should say it that way. That all takes two arguments, right? We're giving it the one and we're applying the second. That's the situation there. So, check nucleotides. But that checks all of them at once, right? Or, yeah. Which is helpful, except that it doesn't tell us... Okay, here we go. What if we did it for a single one? we would do car, and instead of all, we just say lm-atcg, like so. Doesn't like that, so we'll do lm c atcg. Now it's saying, I'll bet it says, oh hey, why can't you do, yep, why not use the infix? It really likes infixes. I actually don't when I'm writing in Haskell, but fine. We'll follow its style guidelines. Okay, and so what we have now is a function to basically do a safety check on each nucleotide in turn. This is really cool because then what we can do, let's get rid of this, is case check nucleotide X of, and we're going to get yelled at here, true, false. So if it's good, then we will continue. However, if it's not, we're going to do left X. And if we do this, we're going to do right. X. Let's see. Why not? If check nucleotide X, then right. Okay. It wants me to do an if then else, but I don't because I actually like the case of here. But this works, kind of. The problem is that right X now if we do RNA X's, we have a problem here, which is, oh, I need the dollar sign, right? Yeah, either car string. So I still can't recurse into this because 2RNA is still giving me back an either. So we have the ability to check a single nucleotide, but unfortunately, and this should be transpose X anyway. This is supposed to be an easy one, and I know that I'm overthinking it. So chat, if you have any suggestions on how we can solve this a little bit easier. What kills me is like I did this 5 years ago, and I just can't. I'm really trying to get back into Haskell. I know how I would do this obviously in Python or other programming languages. But what we're running up against is this right here, is the either. Zemon49, thank you so much for the follow. I know this is like hard and painful, but this is the stuff that like gets you to be a better programmer, is muscling through this. Okay, so we have let's think through in steps. So we need to check each nuke, short for nucleotide. Then we need to, if bad, we're going to left with that car. One way or another, we have to alert back that that character is bad. Otherwise, transpose it, and then move forward, which is what we're doing here. What I need is a way to continue the transposition. Without running into this either problem. The reason I can't go back into this function, as I said before, is that this either type is different than a straight up string. This either can contain either a character or a string. So I'm trying to say combine the transposition of a single character with, you know, running 2RNA against the rest of the string. The problem is that I can't combine a string and an either. And you might think, okay, we'll just write a look ahead and like do a case for each one, but then basically I'm just doing an infinite recursion. I'll be running those checks forever. Nothing will ever actually return. So that's no good. Okay, I think I might have a way to do this that might be a little bit interesting. What we're going to do is we're going to change this up. We're going to do check nucleotides again. We're going to change it back into being a string. But here's the part that's interesting. Or actually, yes, and it returns a character. Here we go. So this is because what we need to do in the case of an error is we need to return that error as a left, right, and a single character. So we need to return whatever that error is. So in order to do that, what I'm going to do is I'm going to write a function that takes in the whole sequence of nucleotides and breaks it down just as we've been doing before. However, it's going to return bad characters when they're bad characters. Otherwise, it's going to recurse onto itself, continuing to check. And if it gets to the end, it returns an empty character, and that will be what we use to check in the 2RNA function to make sure that we're good. I think that'll help us out here. Right. So let's get rid of this. 2RNA X's equals, right. We'll just keep it like this for now, so it's not yelling at us. Now, for check nucleotides, we'll say ends. We're going to do the empty list equals the empty character. Character literals may not be empty. Can I give it an empty string? Ooh, we can maybe... Can we use a maybe? Yes. Okay, so a maybe is another type of monad. But rather than having two types, it has kind of one. So then we're going to do check nucleotides X's. Same thing that we're doing X's. Actually, we'll say N's to clarify. Equals... case N LM ATCG of well, let's write this as an if N LM ATCG, then we're going to do I'm going to do check nucleotides ends else no, I need it to be the character. That's fine though, actually. Else just N. Oh, that was silly. So I had it, I was just justing too fast. So the way this works then is check nucleotides is going to go through every single nucleotide, and for each one it's checking, and if it's in the right sequence, then we're going to continue recursing all the way down, which means that if we get to the empty list, right, if we get all the way down as we split each one off, we finally get to the bottom of the list, and we're passing an empty list, we're going to get to nothing, right? However, if there is a problem with one of the nucleotides, we are returning that inside of this just wrapper, which is how maybe works, which means we can use that inside of our 2RNA to get the character that we need for the check. So what we'll do here is, since we're doing basically a look ahead, is case check nucleotides X's of, and we're gonna parenthesize that. Do we need to? If it's nothing, we're gonna return a right of map transpose X's, which we've already done. And then if it's a just C, we're going to return left C. Ugh. Okay. I don't love the term malding, but I think that certainly applies here. So what we've done is we have run a safety check for our nucleotides, and then we have mapped transpose to do the transformation against all of them. So we're checking to make sure that they're all safe. If they're not, then we're going to return the character that is bad as a left type, and if it is good, we're going to do right. So we are doing recursion. We're just doing it in our safety check rather than in our primary function. And then our transpose is just up here as a helper. We could also have done this as a like if else tree or something, or a case statement down here inside our 2RNA function, but there's no cost really to do it up here, so as a separate function, so I prefer to do it that way. Okay, let's run our tests and see how we do. After all that feels good. So exorcism, submit, source, RNA transcription, DNA.hs, I guess. Now I'm real curious how other folks have solved that one. And yeah, let's view community solutions. And we will, I don't want to search by user. I want to look at, like, you used to be able to sort them by stars. How many people liked them. It doesn't appear to be something you can do anymore, which is unfortunate. Well, let's take a look at one of these and see how it did. Oh, interesting. So map to complement, where to complement A, X on error equals error, invalid nucleotide. I think this is from, yeah, 7 years ago. So the problem with some of the community solutions here is that they used to be a little bit simpler. The puzzles used to be a little bit simpler, especially for things like Haskell. Now that they've introduced things like the either type into their exercises, some of these other community solutions will not apply. Because I was like, yeah, that was a super easy solution. It's the either type that we needed to account for in that one. All right, cool. Now, why go through the trouble of learning Haskell? Why do it? Especially if you're not going to use Haskell in production. Because thinking this way is pretty different. It's not the way that you usually would think about programs, but what you end up with is a very safe and also pretty efficient from a code standpoint kind of program. Even if we were to write something like this in Python, it would be fast. And so getting you to think about types, getting you to think about flow, and making sure that you're handling every possibility of your data is, I think, super, super valuable. Anyone who's watching, this is also an AMA, so if anyone has any questions, feel free to ask away. Meanwhile, I'm gonna try to take on another one of these. Some of multiples should not take long. just knock this out. Although I feel like I got hammered by this when I did it in Rust the other day. Or Nim or something. I can't remember what I was doing, but it was harder than I thought it was supposed to be. Whenever I do programming streams like this, they're always pretty poorly attended, which is understandable. They're not the most exciting, but it's kind of like Al was saying on his stream the other day that he wants to show people like the real process, and that's kind of what I'm doing here. Is, you know, look, it isn't pretty always, right? It's not always like dancing across the keyboard and jumping right at the solution. If it were, everybody would do it. Sometimes you really have to put your head down and think about these things, and that's the reality of it. So this is what you have to do to get good at this stuff. All right, sum of multiples. What are we doing? Given a number, find the sum of all of the unique multiples. Oh yeah, that's right. Of particular numbers up to but not including that number. If we list all the natural numbers below 20 that are multiples of 3 or 5, we get 3, 5, 6, 9, 10, 12, 15, 18. Right. I love this. This is how we're going to do this. This is kind of a cool thing. One of the things that Haskell has in it is something called lazy evaluation, meaning that even large things are not evaluated until they have to be. Hey, Panda Cat. Yes, you gotta love LA traffic. I love that I don't have to deal with it anymore. So, see what I'm doing here is I'm taking 5, basically from the list of 1 to 100, right? So, unique multiples of particular numbers. So what we're trying to do is we're trying to get all the numbers that are multiples of 3 or 5. And so to do that, we can actually run this through a filter. And so if I were to say take 10, right, I get 10 numbers. If I wanted to say, like, get just the even numbers, I could say filter, and I'll do this with a lambda mod n2 equals 0. Awesome. I don't know, it's just something about when Haskell works, it's just so beautiful to me. The way that the functions just mesh together. But so what have we done? We've used filter and our own lambda function. We may be able to clean this up. I think our syntactical helper can help us with that. But basically what we're doing here is we're creating an anonymous function for each number we check to see modulus. This is the percent sign in Python, the modulo, basically the remainder of integer division. And by 2, we can also do this as an infix if we wanted, but I like doing it this way, equals 0, so this returns true or false, and we're filtering for only the things for which it returns true. We could also write that as a function if we wanted to. And take 10, meaning we're going to take as many of them as there are. So we don't actually need even the take, right? So if I just use 1 to 100, now I'm going to get all of the even numbers 1 to 100. So that's kind of it. And oh, they want the sum of the multiples, right? So if that is the case, then we're going to do sum, and then that's just like it. That's, I think, unless we missed something, that's the entirety of our implementation right there. I'm sure I got something wrong there, but I'm pretty sure. Let's check the test to see if we're getting that right. So like 3, 5, factor 3, limit 7. And notice that it includes up to, but not including that number. So we're going to do a -1 somewhere in here. Okay, so sum of multiples, integer, integer, integer. Love it. Factors limit equals. We'll do another fun Haskell trick here, which is we can define functions later, where we're gonna do sum filter filter, yeah, is factor factors, and say 1 to limit -1. A0 integer. We'll kind of work this out in just a second. Filter. Yeah, okay. So first thing we're going to do is say where is factor oh, factors, right. Is factor equals, let's say, is factor n equals, what we're saying is all oh god. I love this hinting though. Turns out there's an even function, but I don't want, okay. Right. Bad. I want mod nf. There we go. And it's not even yelling at me about the application. There we go. So we're saying, give us the sum of the resultant list of taking the numbers 1 to whatever the limit is minus 1, because we're not including that limit. Okay, so this is the list of integers that we're starting with. We are going to filter that list against the function isFactor, meaning making sure that the factors are available to us, or that it's a multiple. Oh, wait a second. Is it 3 or 3 and? 3 or 5. No problem. We'll just change that to any rather than all. So if any of the factors, or if our number here is a multiple of any of our factors, then we are solid. It'll return true. If none of them are, it'll return false. I think that's it. I had one failure, which was a divide by 0. Which we can do as a safety check here. The factor 0 does not affect the sum of multiples. Factor 0 does not accept the sum of multiples of other factors. So we have to handle 0 since they're giving us zeros. Easiest way to do that might be God, I love this. So what we're doing is we're taking factors and making sure that they're filtered to only have factors that are greater than 0. Love it. That's pretty clean, I think. Any questions on this implementation? I know that we kind of powered through that one much more quickly. See what Haskell does when it works with you. So we're taking all of our factors. And we are checking any of them, provided that they are greater than 0. So we're kind of cleaning our factors list for any that aren't 0 to avoid the divide by 0 problem. And we're checking all of our factors. And if the number up to our limit, if any of the numbers that we're checking are multiples of those factors, then we're basically adding it to our list that is the result. And then because we have the sum ability, this actually works the same way in Python, but if we do sum, 2, 3, 1 to 5, right, we'll get 15. So we can do sums really, really easily that way. I think there's also a product. Yeah, there is. Which, product 1 to 5 is the same thing as doing 5 factorial, right? So kind of interesting that way. Okay. This one's done and dusted. Now, just for kicks, I am curious. Did I do this one in Nim? No, I didn't, actually. Let's see what this would look like in Nim, just as a comparison. Oh god, apparently we started it and we never finished it. Oof. Did we seriously not finish it? How do you run tests in Nim? I actually don't know. Nim CR test. There we go. Oh no, we did get it. We did get it right. I guess we never submitted it, though. So what does it look like in Nim, the sum of multiples? Kind of similar. Right? Let's actually do a side-by-side here. So our clean factors is up here, as opposed to where we did a filter for them down here. But very similar approach, where we're filtering the factors to make sure that they are greater than 0. It's just that Haskell makes it super easy to write that, right? A lot less verbose than what we're looking at here. And then what do we do? Here, you'll see that we are looping. So we're using a for loop, which we're in an imperative language. That's not that surprising. But in Haskell, we don't have to do a loop because notice what we're doing. We're doing a plus equals, right? And result is the built-in function, the proc variable inside of Nim. This is a Nim specialty. So procedures or procs in nim have a built-in variable for return values called result. And so you can mess with result without ever defining it in a nim proc. It's built in for you. So I'm taking advantage of that here because it's initialized to 0 basically. And so I'm just like adding whatever I is. What is I? Well, notice that I'm going to from 1 to ceiling -1, very similar to what I'm doing here, right? Where I'm producing that list. The difference is that here I am summing after a check for factorization. In the case of Haskell, what I'm doing is I am filtering the list of factors first, then I'm summing all of those all together. So the reason you don't see a loop is because I am evaluating the whole list first, then filtering that list based on the factor function. I don't know which way is better or faster. A lot of performance questions one way or another, but I have to tell you, I think the Haskell code is more readable. All right, let's try to knock off one more. This is usually the point where I bite off more than I can chew, and I start going overtime and kicking myself. But I don't care. Why can't I just mark these as complete? There it is. Okay, so the UI on this could use a little work. For example, I should be able to mark this as complete from this list. Okay, one more. So many of these are ooh. Okay. This might be a fun one. Hamming distance. More DNA. This up. Oh, hamming distance. Distance x's, distance y's. So basically, what are we talking about here? We're talking about two strings, and the hamming distance is the number of differing positional nucleotides. Ooh, this is a cool one. This is a cool one. Why is this cool? This is cool because if we think about this the right way, actually, we've done folds before, but this is like a manual fold, which might be kind of cool. What is a fold? A fold is where we take a list of things and we compress them into a single value. In JavaScript, it's called a reduce. And in Python, in iter tools, is there a... Accumulate. Gasp. C-Cube Dev. Thank you so much for the raid. Welcome, friends. This is the computer science class that you never had, basically. That's what we're doing tonight. We're doing some programming basics using Haskell of all languages. Now, I realize that we're on the Python documentation, but we're doing a comparison. So there is this function accumulate in Python, which is essentially a fold. Really, really cool idea. And in fact, the filter and the map functions that we've used previously are all specific implementations of a fold, which is kind of the generic definition of this, where we take a collection of things, we apply a function that it takes two values. It takes an accumulator and the next element in that collection, and at the end of the day, what we have is the accumulator value, whatever that thing is. So sum actually is a perfect example. If we were to specifically, or if we were to manually implement sum, we could do something like fold. Actually, can I do type fold? Sorry, fold L for fold left, because we're going left. And this is where Haskell starts, the function definitions start getting a little bit crazy, but kind of cool to read once you know how they work. So basically, what are we looking at? We're saying that, notice that the type constraint is foldable. It has to be foldable. It takes, actually, I'm going to ask you, chat, because we've been looking at some function definitions here. Can you tell how many arguments a fold takes based on this function signature? If anybody's interested in answering. It takes 3. And this is how we kind of read function definitions or function signatures in Haskell. So this is the name of the function. Then comes the either constraints or the argument listing. In this particular case, we have a constraint, meaning that the type T has to be foldable. Whatever we define as T has to be of type foldable. And if we have a constraint, that'll be a fat arrow. Then come the arguments to the function. Now, as I said before, the arguments to the function are separated by skinny arrows. But the last element of the function signature is also separated by a skinny arrow. Why is that true? That is true because of something named after Haskell Curry, the guy for whom the language is named. Which is what Haskell Curry figured out in what he defined as the lambda calculus, is say you have a function that takes 2 arguments. What he figured out was that a function that takes 2 arguments is indistinguishable from a function that takes 1 argument and then returns a function that is another argument the same way. And that's what currying functions is. So basically, we're saying that, this function that takes 3 arguments is indistinguishable from a function that takes, let's say, 1 argument and then returns a function that returns a function that takes another argument and returns that same thing. That might not be a super clear explanation, but basically that's why there's no distinction between the return value here on this right arrow and the arguments, because in Haskell they're the same thing. So what does fold take? It takes this, the first thing you see here is the first argument for a fold is itself a function that takes, right, so, two arguments itself, a b and an a, and returns whatever b is. This is where I was saying the accumulator, right, which is called b here, and then a, and then it has to return b, whatever type b is. And then we have b, which is our starting accumulator, whatever that happens to be. And then a, which is our list of things that we're going through. So, you know, when we talk about sum of like 1 to 10, right? What's actually happening is that this is an implementation of fold. Let's do fold L manually to do a sum. So fold L, the first argument is a function. So we'll give it a function, and it takes n and actually we'll call it the accumulator, and the x, there we go, that's how we'd write that. So x is the element that we're looping through, or the element that we're dealing with at present, and the a is the accumulator. So what we'll do is we'll say a plus x is what the function actually does, meaning we're adding that element, 1, 2, 3, 4, whatever it is, to the accumulator. Then, so that's our first argument to the fold sorted. The second one has to be of type b, whatever the accumulator was. Well, I'm going to start it off at 0. And then the third argument has to be the thing that we're iterating through, which is 1 through 10. See how that works? Now, by the way, if I had started the accumulator at 1, the value is 56. So now I hope that's a little bit clearer how fold works. It takes this special function taking two arguments, one of which is our collector, our accumulator, and one is the current element in the collection that we're working on, and then whatever implementation is, but what we're doing is we're changing the accumulator as we go. We start the accumulator with a specific value, and we give it the collection to work on. That's fold. And once you start thinking about things that way, a lot of stuff starts to look like a fold. So let's go back to our Hamming distance problem here. What do we have? Well, we have a collection of things. I know that for the moment it looks like we have two collections of things, but stick with me for a second. We have a collection of things, and what are we trying to return? A single value, the distance, the number of times these two things differ. Now, we know that they're sequential, and we know that they're... I think the test is probably going to throw us a curveball, like something that has different size. Yeah. Different size strands, which we will handle. However, the basic idea is that we need to compare these two strands. And what if they weren't separate collections? What if we could combine them in some way? Here's the deal. The easiest way to do that is this thing called zip. And zip takes two lists, ideally of equal length, although it doesn't have to be, and also equal type, I think. I don't think I can do like A, B. Maybe I can. Yep, no, that works fine. So zip, notice what we got is a list of tuples, basically, where these are combined. what I can do with that is I can zip my two, right? If I zip these two, I don't need a comma there. Now, all of a sudden, I'm dealing with a single list. And what if I were to do something like, that's my list, right? And what if I did fold L, and what if my function was like accumulator and we'll call it a xy. We'll say if x equals y, then a, then a, else a plus 1. So we're using the parentheses here to deconstruct this tuple to get the x and y. And fold, don't forget, requires a starting point for our collector. That's it. That's it. That's the entirety of this this problem. Now, there's something like knocking around in the back of my head that there's another, and I don't entirely. Oh wait, I don't have to search in Google for this. Type zip width. ABC returns. So zip width takes a function, notice. And to oh, this is a cute way to do it too. So we'll do it both ways. The first way we're going to do it is, so you have x's and y's. We're going to say what do we want to do for unequal lengths? Yeah, so these are all nothings. So if let's just make sure that we're using length correctly here. Cool. Oh, right. It's not bang equal in Haskell, it's slash equals. Because they couldn't be normal, could they? Nothing else. And now we get to implement this. We're gonna say just because it has to be yeah, just because we're gonna do maybe. And then what are we adjusting? We are adjusting fold L. And what are we folding? We're folding with a function. Takes an accumulator and the current element we're working with. Except the current element we're working with is a tuple, so we're going to break that down into an x and a y. And what are we doing with that x and y? We're saying if they're equal, if x equals y, then a, else a plus 1. That's our lambda function. That's what we're folding with. And then we have our accumulator. And then what are we starting with? We're going to do a zip of x's and y's. That's the first way to do it. I think that's pretty much done here. Let's run that and see what happens. Okay, easy enough. Now, if we wanted to use zip width, what would that look like? Well, what is zip width? What was I doing with that? So zip width is kind of cool. Zip width takes a function that takes two arguments, very much like the collector for fold, right? But then it takes two lists, and then the result is C. So the other way we could do this is instead of a fold L, we would say something like, actually, let me comment this implementation out. We'll do just zip width, and here, very similar here. So A, B of type C. So what we could do is write X and Y and say if X equals Y, then 0, else 1. Then X is Y's. Then we are summing that value. So it's slightly shorter. We're still doing a comparison there. But see how with zip width what we're doing is we're actually creating a new list where we're taking these two, and the result is not the comma, it is this function that applies and creates this new value. In this case, we're turning it into an integer, 0 or 1, right? And because it's 0 or 1, then we're just going to get like a bunch of 1s and 0s, which we're going to just pass over to sum. So both of these should work. Let's try it with the zip width and see what happens. Cool. Works the same way. I'm curious, which one was faster? Zip width was slightly faster. The first one was 0.0043 seconds. The second one was 40. 40. Let's see if that holds true. Ooh, now that one was 3.8. 5.2. I mean, it's all over the place. It doesn't really matter. But, you know, pick your poison. But either one of these actually works fine. I'm glad I was able to redeem myself after pulling my hair out on the first one. able to knock these two out in pretty rapid succession. So, I mean, again, I think there's a lot to like in Haskell, especially as a teaching language, but it turns out, to bring this back around to our security mission, turns out there's actually a really nice Windows 32 API library for Haskell, which I was shocked to discover. For example, if we go to win32.process, there is indeed, there's like create process. There's even, I'm pretty sure there's a create remote thread in here somewhere. Point is, we could actually write a wrapper for like a interpreter shell or something like that, if we wanted to. Pretty crazy, but it is true. So, more powerful than people might give it credit for. Alright, I think that's going to do it for tonight, friends. Thank you so much for hanging out. I hope you learned something. I know that I did. But, let's check out the hack list to see who else is streaming right now. Perfect. So, if you don't know about the hack list, here it is. Actually, I should have done it. That was a dumb way to do it. Here's the hack list. We have two kind of versions of it, and if you're interested in InfoSec streaming, then lots of things to check out there. But I think we're going to give Jay Beers a raid. So I will be back on Saturday doing some blue team stuff. We're going to continue the build out of our SOC lab. But until next time, be good to yourselves, be good to each other, and happy hacking.